All right, so that is our first energy balance. So what we've done is we've constrained the temperatures and we solved for the airflow. And now this is going to rattle through, like everything else has to obey, that airflow. So as an example, the afterburner, one of the open questions here, temperature in stream 8. So stream 8 is going to come out hotter than stream 6 or 7 because of the additional combustion. It's basically an adiabatic flame temperature calculation. We're taking input gases, we're taking their flow rates. So we have the nitrogen and oxygen coming in the air. We've got the hydrogen and H2O that are coming in the unreacted exhaust. So here's our 0.2 of a mole of hydrogen that's left over. And we're going to burn all of it up. So we're going to go from 0.2 to 0 hydrogen. And then we're going to go from 0.81 water to 1.01 water because we're going to use up all the rest of the hydrogen. That will use up a little bit more oxygen. Also, the nitrogen comes through. So in this case, the incoming enthalpies are just the ones that we just already calculated because they're the ones coming out in stream 6 and 7. So these inputs are the same outputs that were up here. And then for the outputs, that's where we have to introduce another unknown. So what I don't know is the temperature of stream 8. I know all the flow rates, but I don't know the temperature of stream 8. So that's why this over here is in red, because I'm identifying that as another iterative variable that I'm going to adjust until this energy balance is met. So imagine there was no change in temperature. I just go through the afterburner with no change in temperature. I burn up all this extra hydrogen. Well, I'm going to be way in excess in terms of the thermal energy. So that's why this temperature has to be hotter, because it has to carry that extra thermal energy. And do the same thing. So I can go to Tools, Goal Seek. I'm going to set that to 0 by adjusting the temperature. And bloop, gives me 0. So now I've basically found out that I'm going to have about 100-degree increase in temperature as a result of the combustion following the fuel cell. And that is a function of utilization. So for example, if I change the utilization to some other number, I can reduce that afterburner increase, right? So if I set this at, for example, 90% utilization, now our energy balance on the stack is off. We have to recalculate the airflow. Cell Q3120 by adjusting the airflow. Okay, so now we need more air. If we look at this balance, it's off again by a wide margin. So goal seek, I want to set that to 0 by changing the temperature. Okay, so now I have both energy balances obeyed again, and now we see the flame temperature is closer. So temperature is still hot, but it's not as hot as it would be if we're operating at lower utilization. Okay, so let me set this back at 0.8. I think we've got the fuel cell and the afterburner solved. The next thing is these two heat exchangers, and just so you can see what the degrees of freedom are here, we've already calculated the temperature and flow rate of stream 8. And we know the temperature and flow rates of streams 2 and 3 already. So the only thing left is what is the split? If we split it by a certain amount, some of it goes this way, some of this goes this way. We now have the temperature and flow rates in streams 9 and 10 after specifying the split. So the only thing left is what is the unknown temperature of streams 11 and 12. And that's what the last does. So I'm going to put this back at 0.07 because I played with this earlier. And hopefully this should go back to 0. Yeah. So again, if we adjust the outlet temperature of the heat exchangers, so I've basically set this up with the heat exchanger outlet exhaust temperatures to be unknown. And then we're adjusting those temperatures in order to get 0 energy balance on each heat exchanger. And that basically allows us to solve for the exhaust temperature. So what it's saying is that with this split, I'm going to get an exhaust temperature of 621 Kelvin and 628 Kelvin coming out of streams 11 and 12. And that's why I've adjusted the split to be 7%, because I want these two temperatures to be kind of similar to each other. And then finally, the last step is kind of trivial. I'm basically taking the two streams, the two exhaust streams, and I'm combining them together and recalculating the temperature of the final stream, which is going to be some kind of average. It's be a molar weighted average of these two streams. Or you can do it as a formal energy balance. So by the time we're all done, these should all be 0. The one thing I do like to do with calculations like this, just to make sure that I didn't have any bugs or errors in here, it won't guarantee it, but it's a good thing to check, is the overall balance. So just look at the inputs, what are the outputs, what are the enthalpies, how much electrical power are you generating. If you did everything right, it should balance to 0. And that's what this is. This is just a straight up calculation of n.h in minus n.h out for the fuel in the air and the exhaust, and the electrical work that we're producing should be 0. Oh, that's back to 0. Okay. If we now kind of like, what is the bottom line of all this? Like, what have we found out from this? One thing I think it's important to point out, the exhaust temperature is quite significant. So by the time we're all done, even though we're preheating the air, we're removing as much thermal energy from that exhaust as possible. We're still, at the end of the day, we have to get rid of the thermal energy that this process is producing. It's producing electricity. It's also producing thermal energy. And the only place for that thermal energy to go is the exhaust. So we've got an exhaust, something more like 350 degrees C, which is quite hot, right? So you could imagine, could we make this process even more efficient by doing something with that thermal energy? Could we take that thermal energy and generate more electrical work? Like, for example, could you just boil water and create a steam bottoming cycle? You run the steam through a turbine engine, you generate more electricity. On a small scale, you're probably not going to put a steam engine on a power unit that's sitting over a rack of computers. On the other hand, if you're doing this on a reasonably large scale, then it might become cost effective to combine this in a combined cycle where you take, steam engine and you get even more electricity out of it. That's a relatively cheap thing to do if you're going up to, hundreds of megawatts kind of power levels. As we'll start talking about next time, how do you do this with hydrocarbons? Like if you're starting with natural gas or some type of synthetic fuel, doing CO2 capture and fuel generation, how does that change the situation? And also, how can we squeeze as much power out of it? Steam bottoming cycle is one idea, but there's also other things you can do too, where you try to use the higher temperature exhaust coming out of the fuel cell directly in a gas turbine engine, where you get even higher efficiencies because you have the much higher gas temperatures. So as we go through the next couple of days, I'll talk about this in more detail, and we'll work out how do you do energy balances with reforming, and how do we squeeze out that last bit of efficiency if we can.